get going here. Um, and Bob, if you would be kind enough to look for John and Kim, anybody else who shows up late, I'd appreciate it. Um, and can everybody see the chapter 4, part 3 of 3 slide?
Yep, we
Okay,
can.
good. We are in good shape then. So we're going to talk about rectifiers and power supplies first.
Hmm.
This week is going to be this week is a real grab bag of stuff, but it is practical knowledge on the technical side of things. So um, sorry, all your ham radio gear uses DC power of one sort or another. For portables, it's for portable HTs, it's batteries. For for transceivers, for mobiles or what you have at home is generally a power supply that changes AC from the wall socket into DC. Um, most amateur radio equipment that is not it doesn't have self-contained batteries uses a nominal 12 volts, um, which is really 13.8. And this is the same voltage as your car battery. Um, excuse me. And we'll talk about the range of voltages over which equipment will work in a bit. But uh, excuse me. But at any rate, so we're going to go into a little bit of detail about how power supplies work. Now, how do you convert AC to DC? Well, first of all you have to step the voltage down to something that is useful for your gear because your gear does not run on 110 volts DC. It runs on 13.8 or 12. Everybody says 12 volts. Um, so usually a step down transformer followed by a rectifier, which changes AC to DC, and then and then at the very least a filter, but usually also a voltage regulator that that the filter gets rid of any AC components or ripple, and the regulator will make sure that that the output is at a set voltage, usually within 1 or 2%. So we're going to talk about rectifiers here first of all. So uh, there are uh, um, half wave and full wave rectifiers. What that means is if you look at figure 424 there at the top, you can see that there's a sine wave coming in, AC input, and um, and then and then on the right hand side is a diode. So that diode only conducts when the top of the transformer is a positive voltage and the bottom connection to the transformer is at a negative voltage. So what that means is you get an output waveform like the one at the top right there, where just the positive halves of the AC cycles get through the diode. Um, Now, that's a little bit inefficient because you're basically not using half the power that Detroit Edison or your power company is sending you. So if you look at the second diagram, if you look at the bottom diagram, there are two diodes and the transformer has a center tap. So what that means is uh, for half the cycle, compared to that center tap, the top connection to the transformer is going to have a positive voltage and the diode will conduct. And the bottom diode there, the bottom connection in the transformer is going to be negative compared to that center tap. And so the diode on the bottom will be reverse biased and will not conduct. And then when you go to the negative half cycle of the AC input, the top diode does not conduct and the bottom diode does conduct because um, the top terminal is going to be more negative than the center tap, and the bottom terminal is going to be more positive than the center tap. And so that center tap acts as a return um, for the voltage to complete the circuit on the secondary of the transformer. And you get a waveform like the one at the lower right on the output of the rectifier there. And uh, it contains half cycles of AC all going positive. In other words, no negative voltages there at twice the frequency of the input because you're basically folding over the negative half cycles. Now you can get, oh, okay, there we go. So in the half-wave rectifier, you're only using or 180 degrees of the sine wave, and the full wave rectifier, you're using the full 360 degrees. Now we can also get rid of the, oh, okay. So this just repeats what I just said, but you can get fancier here. You can get rid of that center tap by using uh, two pairs of diodes. Now, if you look at this, imagine that sine wave on the AC input. So when on the positive going half, the top terminal is going to be more positive. So diode D1 conducts and current flows through the load and then it returns through D3 to the bottom terminal of the transformer. And then um, when the pardon me, when the AC input is in the negative half cycle, then the other two diodes conduct. So when the bottom terminal is positive, D2 conducts, current flows through the load, and then current flows through D4, which goes to the top terminal of the transformer, which is negative. So on the right, you can see, this is kind of a funny diagram, but what you can see is the pairs of diodes conduct on alternate half cycles. So 1 and 3 on the positive half cycle and 2 and 4 on the negative half cycle. And I would ignore the bottom half of that graph because because no current is flowing through the diodes in the reverse direction. Now the difference here is that between this circuit and the full wave rectifier in the previous slide is that the transformer does not need a center tap, which means you basically save half the wire on the secondary. But because there are two diodes in series with the load at all times, the voltage drop is going to be two diode drops or about 1.4 volts, whereas it's only 0.7 volts in the full wave rectifier. And but for the full wave rectifier and the full wave bridge rectifier, you get peaks at twice the input frequency, or 60 hertz from the power company, it's going to be 120 hertz peaks here. Now generally, for uh, um, pardon me. Generally, it turns out that transformers are more expensive than diodes. So it's more common to see this full wave bridge rectifier. Uh, but it boils down to it boils down to cost. Whichever is less expensive is what's going to be built into the power supply. So now we've got this output from the rectifier that has a lot of ripple in it. In other words, it's not a steady voltage. So then we need to send it through a filter. Oh, okay. All right. This illustrates what I was talking about. When the top terminal is more positive, D1 and D3 are conducting. And when the top terminal is more negative on the right-hand side here, D2 and D4 are conducting. So the diodes with black bodies are conducting here, and the diodes with white bodies are not. Oh, we've got somebody else. We've got John, I bet you. Yep. Okay. So anyway, well now you want to get rid of all the ripple. So you want to get rid of the variation in the voltage so that you have a very steady voltage going into your transceiver and no hum. So so um, you want to use a filter network, and you want to use a filter network, and it can be capacitors or capacitors plus inductors. And oh, okay, so the way this works is usually a capacitor will be connected between a capacitor will be connected between the output and ground. And so the plates of the capacitor act as a reservoir of charge. So that for some of the cycle, for some of each half cycle, um, the capacitor will be adding charge. So some current will flow through the capacitor and some to the load. And then on the negative half cycles, or I'm sorry, so going up toward the peak, the capacitor will charge, and as the half cycle goes back towards zero, the capacitor will discharge. Now, if you put a choke in series, if you put a choke in series with the rectifier of the output of the rectifier, that will tend to block AC by converting it by converting current into a magnetic field. So what you have with a filter inductor is the magnetic field is constantly increasing or decreasing, and as the magnetic field decreases, it sends current out of the coil or inductor. So um, depending on the circuit, and again depending on cost, you may see only capacitors, or you may see capacitors and coils, capacitors and inductors. And in this case, when you're trying to choke off any AC ripple, the inductor is called a choke. All right, so let's talk about safety here. Now, it turns out that power supplies, even as low as 12 volts, can be dangerous because if you are the conductor, if your body is the conductor between the power supply output and ground, uh, you can the shock, the current that flows through your body can damage it can damage it. You can run into trouble. So uh, so this is more important for high voltage power supplies, but bleeder resistors, you'll see a high value resistor placed across the output from the positive voltage to ground. And what that does is usually when the power supply is running, it doesn't conduct much current. But when the power supply is turned off, there's still going to be charge in the output filter, in the capacitors in the output filter. And so the bleeder resistor will bleed off that charge so that the capacitor retain it. Um, and then you will also want to protect against drawing too much current through the power supply. So usually, and this occurs either when you're trying to draw too much current from the power supply or when there's a short circuit on the output of the power supply. Well, the fuse on the wall socket side, the primary side of the transformer, will blow when you try and draw too much current. And so what you'll see in most amateur radio power supplies is a fuse and is a fuse on the back, or occasionally you'll see circuit breakers, but those are for safety. So uh, fuses are to protect the power supply while it's operating. The bleeder resistors are there to protect people from either high voltage or from stored energy when the power supply is turned off. Well, let's talk about switch mode power supplies for a second. Most power supplies, including the wall warts that you use to charge your phone, and you connect to various pieces of equipment, they use switching power supplies. And the way a switcher works is very interesting. The AC on the input is first rectified and filtered, but not regulated. And then a transistor switch pulses at high frequency. Oh, and the AC, when it's rectified, is still going to be close to 120 volts. 120 volts peak on the output. Transistor switch pulses at high frequency to transfer energy to a filter capacitor, and the pulse width determines how much current flows to the capacitor. And the frequency can be anywhere from 20 kilohertz up to a few megahertz. And as a matter of fact, you can run into problems because a, a switch mode power supply can cause RF interference because of this switch transistor. Um, at any rate, the the high frequency the high frequency switching allows the power supply to change its output current very quickly without much change in the output voltage. And it also means that um, you can use smaller inductors and capacitors in the filter because the frequency is higher. If you remember, reactance goes inductive reactance goes up with frequency. So the resistance, the opposition to AC in a series inductor would go up, and um, in a in a capacitor, the reactance goes down with increasing frequency. So as the frequency you're trying to filter out, the ripple frequency you're trying to filter out gets higher, you can use a smaller value capacitor to get the same amount of filtering. So this is a diagram here. It's in your book, and so in the upper left here you have a bridge rectifier and filter capacitors. So you have 120 volts without too much ripple, and then you have a switching transistor or multiple transistors that drive a transformer they drive a transformer um, to to step down the voltage usually, sometimes to step it up. Um, and then there's a second rectifier stage that operates at high frequency, and then capacitors and sometimes inductors for an output filter. And then looking at that DC output, there's a feedback path. What's called a switching control circuit here acts as a voltage regulator so that depending on so it increases or decreases the width of the pulses that turn on the switching transistor, depending, so that, pardon me, so that the output of the power supply, the DC output at the lower right there, remains fairly constant uh, for various amounts of current drawn through the from the power supply. Okay, so we're going to do some practice questions here. So let's see, how can I get my video back here? Here we go. I apologize. I do not know why my camera keeps cutting out. So what is the function of a power supply bleeder resistor? I will be happy to take guesses.
B.
That's right. It's B. Look, hello. It's B. Why is this not working? The answer is B. Yes, it discharges the filter capacitors when power is removed. Now, remember, I said that the bleeder resistor had a fairly high value, so it can take several seconds or many seconds for the for the output voltage of the power supply to sag down to zero. But it's a good safety precaution. Which of the following components are used in the power supply filter network? Diodes, transformers, and transducers, capacitors, and inductors, or all of the above? Anyone?
D.
Capacitors.
I'm sorry, did I hear D, delta?
Yeah, yeah.
Okay, no, the answer is for the filter, for
Oh,
the
for the
network,
filter.
we use
Okay.
capacitors and inductors, letter C.
Yeah. Yeah, I didn't read it closely enough. Okay.
What type of rectifier circuit uses two diodes and a center tap transformer? Full wave bridge, half wave, or synchronous?
Half wave. C.
I have a C. Anybody else?
Full wave.
Full wave. Yeah. I was thinking four. You don't use all four at once. That's what it
No,
got
no.
me.
Only two diodes and a center tap. That would
Yeah.
be B. Oh, sorry, that would be a full wave, A.
Yeah.
Yeah. So two diodes, it's the center tap that gives it away. That's a full wave rectifier. What is a characteristic of a half wave rectifier? A, only one diode is required. B, the ripple frequency is twice that of a full wave rectifier. C, more current can be drawn from the half wave rectifier. Or D, the output voltage is two times the peak input voltage.
A.
Yes, the answer is A. Only one diode is required. What portion of the AC cycle is converted to by a half-wave rectifier? 90, 180, 270, or 360 degrees of the sine wave?
B.
Yep. B. 180.
That's right, B, bravo, only half of the sine wave. Whoop, here's Kim. Let's let her in. Okay, good evening, Kim. Hi, we've gone through power supplies and we're just doing questions on power supplies. There we go. Oh, okay. Well, I just gave the answer to that. What portion of the AC cycle is converted to DC by a full wave rectifier? And same choices.
E360.
That's right, 360, because diodes conduct during both halves of the AC input cycle. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? Series of DC pulses at twice the frequency of the AC input. In other words, they don't go negative, they only go positive. Series of DC pulses at the same frequency as the AC input. Sine wave at half the frequency, or a steady DC voltage. Anyone?
I'm gonna
Twice.
guess C since they talk about waveform. Maybe not. That's just a guess, though.
It's either A or B. I think it's A.
A, A.
And the answer is A. Yes, you get
Uh,
you get pulses. You get. I think using the term DC in here is a little bit confusing, but the idea. Usually, when we say DC, we mean a steady voltage, but direct current here means that the voltage only goes in one direction, and we're just arbitrarily calling it positive when we look at circuits. Which of the following is a characteristic of a switch mode power supply compared to a linear power supply? Faster switching time makes higher output voltage possible. Fewer circuit components are required. High frequency operation allows the use of smaller components, or switch mode is inherently more stable.
C.
yeah, I think it's C.
Yeah, the answer is C, Charlie. If you look at old ham radio gear, you'll see big transformers in it. And if you look at modern ham radio, well, if you look at modern power supplies, you'll see much smaller transformers. So smaller values and physically smaller too. Switch mode power supplies. Well, if you look at your phone charger, it's something you can easily hold in the palm of your hand. It's the size of a small box of matches, maybe, and it's capable of outputting several watts.
They're lighter too.
Okay, so we're going to talk about batteries for a little bit.
So, quick question.
Please.
I have a battery lawnmower, and it comes with a very nice 65 volt, 5 ampere hour battery.
Yep.
And the company also sells inverters. And I thought, well, this is a great way to have remote power when I'm working one of these races or something. So I initially bought one that was rated a little lower, 200 watts, I think. But that one was not pure sine wave. So certain things like a stereo, to use a stereo remotely, it would not work. So then I had to buy a more expensive one that was 400 watts pure sine wave,
Mm-hmm.
and everything worked great. And I was just trying to, envision how these things work. I assume there must be a transformer in there to get it from 65 to 110, and probably something like these switching transistors they somehow use to get it from DC to AC.
It probably is a switch mode power supply of some sort. And there was an article in QST magazine just a couple months ago. Some people are using these power tool batteries with with DC to DC converters to power their rigs. So
I've heard that.
yeah, so you get a switch mode power supply in one of these gadgets that converts your 65 volts DC down to 12 or 13.8. And people use that to operate portable in parks, for instance. So yeah, as a matter of fact, that is a real thing. Um, and and again, small size and small size and small physical size and uh, smaller value components are why a lot of people are why switch mode power supplies are so prevalent today. And they only switch mode power supplies, I think I remember. Um, I would say back in the early 1980s is when you first started seeing a lot of them. So they've been around for a while, but uh, it's sort of the fallout from going from tube gear to transistorized gear, and as a matter of fact, it sort of follows the development of power transistors capable of handling many amperes. Anyway, let's talk about batteries for a little bit. Um, this is a fairly arbitrary distinction, primary and secondary batteries, but one way to think about it is uh, that that uh, that primary batteries, think of it as something that goes inside a piece of gear and powers it directly. So most of them are one-time only use. Carbon zinc or alkaline batteries are the common AA through D size cells that you get at the drugstore. Silver nickel cells, I believe, are hearing aid batteries. Or if you have a thermometer or some little gadget that fits in your hand, those coin cells, I think, are silver nickel. Uh, they're preferable to secondary batteries because you may not get a chance to charge batteries in an emergency. So secondary batteries can be charged and reused many times, and usually they're larger than primary batteries, uh, and they also have much higher capacity than primary batteries. So some of the chemistries, nickel cadmium, nickel metal hydride, lithium ion, and the oldest technology is actually lead acid. So that's your car battery, is a lead acid battery. NiCads were very popular in handy-talkies, but it seems like these days the batteries are getting smaller and the what's called the power density, how many watt hours per ounce you can get or per cubic inch you can get, are going up with these newer chemistries. Well, so this is a comparison chart, and you can see the different output voltages. You can see the different uh, energy ratings, and batteries are usually rated in ampere hours, or for smaller ones, milliampere hours. In other words, so many milliamps for 1 hour, or some fraction of that. I'm sorry, the product of time plus time and current is ampere hours, and that is actually energy capacity. Well, let's look at storage batteries. We use them for emergency or portable power. If you have I'm trying to think of the name for it, but some people have uninterruptible power supplies. So if the AC power goes out, you'll still have power for 10 minutes or half an hour, or perhaps even longer. And those work because they have batteries inside. So the battery is kept full charge, and then when the AC power goes out, when there's a blackout, the battery switches into the circuit and powers your computer or your gear for long enough that you can either shut down your computer or the power comes back. Anyway, storage batteries are used for emergency or portable power because there's no AC. And uh, these chemistries are all actually uh, traditional batteries. It turns out that you can make them somewhat lighter and somewhat more rugged by not putting acid in them, but instead using different electrolytes. And these gel electrolytes have the advantage that you can't spill them out of the battery. So most of these are rated as 12-volt batteries, but they're actually 13.8 volts. And this goes back to automobiles. And it turns out that your ham radio gear that's rated at 12 volts will work at 13.8 just fine. And that's where most people set their AC power supplies to 13.8 volts output. Now, lead acid batteries can produce power down to about 10.5 volts. And so a lot of equipment, including the electronics in your car and including most ham radio transceivers, will shut down if if the input voltage goes below 10.5. So, and if you deep discharge a battery, in other words, run through almost all of its capacity so that it has only a small amount of charge left and the output voltage is very low, that will shorten the battery life. So instead of several years, you may get only one or a few years. Okay. So batteries are rated by the amount of current you can draw from them. And the less current you draw, well, batteries work by chemical reactions. So the less current you draw, then the slower the chemical reaction needed. And because these are chemical reactions, they produce heat one way or the other, either charging or discharging. So if you limit the amount of current drawn and keep it well below the maximum discharge rate, then your battery stays cool on the inside and you won't damage it. Some battery types are designed to have high discharge current, and so there's an equivalent internal resistance in a battery. And if that's low, for instance, with NiCads, you can get high discharge currents. Now, lead acid batteries are also designed for a high discharge current. If you think about your car, when you're cranking the starter, you might be using 100 amperes, but you don't do it for very long. So lead acid batteries can withstand that. NiCads and some other types can stand brief episodes of high discharge current also. So batteries aren't perfect. You lose some because they depend on chemical reactions. You lose some electrical energy to heat, and also when a battery sits there, not even connected to anything, it will self-discharge, and you'll slowly lose the charge in the battery. Some batteries are very good at this. For instance, coin cell batteries will last. It's very common for a coin cell to last a year in something like a thermometer because it's not used partly because it's not used very much, and partly because it has a very low self-discharge rate. Your car battery Your car electrical system is designed so that you can park your car for a month and still start it. Well, in good weather at least. Um, and I say this because I actually ran into this on the job. So the idea is that all batteries will lose charge eventually, but some of them are built. Some of them have a designed-in self-discharge rate that's kept low deliberately, or is compensated for. Now, when you store batteries, you want to keep them cool and dry, but keep them above freezing. Um, partly because you can run into trouble uh, because water or liquids expand when a lot of liquids expand when they freeze, uh, and some of it just to treat your battery nicely. Well, okay. The other forms of power you can use are one of them is solar power, and um, solar cells are a special kind of diode that convert light to electricity. Now, this is the opposite of a light emitting diode that converts electricity to light. We have Albert Einstein to thank for this because he was the first who figured it out that you could turn photons into electric current or vice versa. So um, so the forward voltage of a solar cell is usually about half a volt. It's called the open circuit voltage, and it does decrease when you're drawing current. Um, Half volt is why you connect a lot of solar cells in series to get a high enough voltage to deal with. Now, solar power systems and wind power systems, because sunlight is not constant and because the wind is not constant, generally require a pretty good battery pack. Um, now, to power a ham radio station, a 100-watt transceiver, you can probably get away with a 100-watt-hour battery system because you're not going to be transmitting a lot of the time. Your radio is going to be turned off a lot of the time, and when you are using it, you're going to be listening at least as much as you're transmitting, which means that the high power draw only happens intermittently. Um, for for a house, a typical family uses, I think, on the order of 11 kilowatt hours per day. So when you see solar cell installations that power houses, you're going to see battery storage. If it does use battery storage so it can stay off the grid, you're going to see battery storage uh, of about that rough order of magnitude. 10 kilowatts and up. This is why off-grid solar power uses such a big bunch of batteries. Okay. Um, lead acid batteries can stand can stand a lot of abuse in terms of the voltage across them, in terms of how they're charged. Other battery chemistries, and in particular, lithium iron phosphate or LiPo batteries, require the use of a charge controller because it's possible to damage them if you charge them wrong. And the idea is that you have to taper off the charging current when the battery gets to full charge. So, so it's usually a good idea to use a charge controller between a solar installation and storage batteries. Also, for solar cells, you want to make sure that when the sun isn't shining and batteries aren't generating, sorry, the solar cells aren't generating electricity, you don't want current to flow backward from the battery through the solar cells. So you put a diode in series so that so that the current will only flow from solar cells to battery and not in the reverse direction. And this is a safety feature. So so to get enough voltage to run a charge controller or an inverter, you'll see that solar panels have a lot of these 1/2 volt cells in series, and to get the amount of current up, you'll see these series strings of solar cells, several strings connected in parallel, so that the current output of the solar panel will be higher. Oh, okay, that's really all we've got to talk about here. When we do field day, one of our club members usually brings solar cells, and he makes a few contacts running off solar cells that are, I want to say, about the size of an unfolded Amazon box, or an unfolded banker's box. You really don't need too much. You really don't need too much in the way of solar cells these days to get on the order of 100 watts out. Okay, so let's do some practice questions here. In what configuration are the individual cells in a solar panel connected together? What did I just say? Anyone?
You just said series parallel.
Yeah, series parallel. So you see series strings of solar cells, and strings are connected in parallel. What's the approximate open circuit voltage from a fully illuminated silicon photovoltaic cell? In other words, a solar cell. 0.02 volts, 1/2 volt, 0.2 volt, or 1.38 volts.
You just said that one too, 0.5.
Yeah, good.
Well, this was a short chapter, so I can remember.
Yeah, there we go. Why should a series diode be connected between a solar panel and a storage battery that's being charged by the panel? To prevent overload by regulating the charging voltage, to prevent discharge of the battery through the panel when there's no illumination, to limit current flowing from the panel to a safe value, or to prevent damage to the battery.
B.
That's right, B, to prevent discharge in the wrong direction through the solar cells. What precautions should be taken when connecting a solar panel to a LiPo battery? Ground the solar panel framework, ensure the battery is placed terminals up, series resistor must be in place, or solar panel must have a charge controller.
D.
That's right, D delta. By the way, this is not going to be anywhere on the test, but most people use charge controllers anyway, regardless of what type of batteries they use for storage, because there's a combination of voltage and current where solar cells put out their peak output power, and some charge controllers are smart about that, and so they can change the load on the solar cells to maximize the energy generation. What is the minimum allowable voltage for maximum life of a standard 12-volt lead acid battery? 6 volts, 8.5, 10.5, or 12 volts?
C.
Yeah, 10.5.
Yep, C, 10.5. Yeah, you guys are good. What is an advantage of batteries with low internal resistance? A, long life, B, high discharge current, C, high voltage, D, rapid recharge.
B.
That's right, B, high discharge current. Okay, now I'm going to talk about connectors. You will use a lot of connectors in ham radio. Hmm. So I'm going to go real quick through the components of connectors because I think most of these you already know. Um, pins are the male pins are the male pieces of metal that stick out from a connector. Sockets are the recessed contacts uh, or female contacts. Um, when we say contact in a connector, that means a pin or a socket that makes physical contact with a mating piece and conducts electricity. Keyed connectors, some connectors you can only insert in one direction. Pardon me, you probably do this all the time with USB connectors. Before USB-C, a USB connector would only go in one way, and probably half the time you and I um, would try and put it in the wrong way and go, oh, and turn it over. So it would go in correctly. So keyed connectors make sure that the connector is oriented in the proper direction and the pins line up the way that they should. Uh, Plugs are installed on the ends of cables or receptacles. Receptacles with a C are connectors installed on equipment. Um, adapters adapters are short cables to go between two different two different types of connectors, they are um, or they are built all into the same shell, so that you just have a little plastic shell with two different types of connectors inside. Those are very common for those are very common for changing between different types of USB connectors. In the early computer days, you would find adapters to connect different RS-232 cables together, or connect when you had an RS-232 cable that was the wrong sex or uh, had the wrong connections. I don't know how many of you remember null modems, but those were little gadgets with 2D connectors um, that would reverse the transmit and receive wires, so that uh, two computers or a computer and modem could talk to each other. A splitter, a splitter divides signals between two connectors, and those are most common for things like headphone cable splitters, audio cable splitters, where you can plug two sets of headphones into one headphone jack by putting one of these splitter cables in between. They're also called Y cables because of the shape. Now, these are all in your book. These are some types of connectors. Um, on the left are power connectors usually used for DC. And I'm sure you've seen and used most of these now. Molex connectors, you'll see those on the back of HF transceivers, and that's the way um, there are individual pins with one wire each that go in the body of one of these Molex connectors. And so you'll see connectors with several wires going in for power or for signals, and sometimes they'll be empty. There'll be locations with no pins in them. Um, terminal strips, terminal strips, you've seen where they're used to screw the ends to connect the ends of two or more wires together, and you use them to connect individual wires from cables together, which is why there are often several of these uh, terminal pairs on a strip. Banana plugs, banana jacks, binding posts. Banana plugs will go into banana jacks, and they usually go on the end of binding posts. And you can also connect wire to binding post by wrapping it around the post and tightening down the top. These coaxial power connectors you're probably familiar with from laptop computers and miscellaneous electronics. And power poles are used in ham radio gear a lot these days because they're designed to carry high current and they're very convenient to connect and disconnect. Now, on the right, you'll see different terminals and connectors that go on the ends of single wires. These quick disconnect terminals on the upper left of figure 429 mean that you can connect wires together and pull them apart very easily. These ring and fork connectors are designed to go around terminal posts, and instead of wrapping wire around and then watching it spread out as you tighten it down, instead the wire is connected or crimped into the end of the terminal, and you have a nice flat prongs on the terminal that mate very well with screws and washers because they're very two-dimensional. So Anderson power poles are fairly standard, and they come with different current capacity, different current carrying capacities, but people usually use 20 and 30 amp connectors. And once they're mounted, they're very convenient because they're easy to connect and disconnect for equipment. Some ham radio equipment comes with Anderson power poles on the back panel for power inputs, but it's more common that you'll see power pole connectors in power distribution blocks. So if you have a bunch of equipment running off a single power supply, this is a very convenient way to plug things in and make one power supply drive several pieces of electronics. Now, power pole connectors and the crimp terminals or the lugs that you saw on the previous slide are done by crimping together. In other words, applying pressure to the metal shell of the connector so that it makes a solid physical contact with the wire that it's connected to. And the idea there is if you have a very firm connection, you'll have a low resistance, and because it is metal to metal surface pressed together, and the metal is deformed somewhat, you won't get corrosion between the wire and the terminal. If you have cable TV, the F connectors on that are usually crimp connectors. So the cable TV guy comes in and he has a special tool, and boom, boom, he strips the end of a coax cable and puts one of these things on all within seconds. What this means, though, for crimp terminals, different kinds of crimp terminals need different tools, and some of them are quite specialized. So let's talk about audio connectors. It used to be that hi-fi the hi-fi audio equipment used phono connectors, which are at the top center, and those are monaural. And so for stereo equipment, you would need one for each channel. Ham radio gear uses phone connections for headphones. And those come in quarter-inch size. Those are older, and those have been around for a long time. But in the last 20 years or so, people are using much smaller connectors. If you think about your earbuds that plug into your phone, those have miniature phone connectors. The difference between phone and phono is that phono connectors go back to phonographs and hi-fi. Phone connectors look more like the connectors on a phone switchboard. Phone connectors can carry can carry 2 channels of audio on 3 wires, or can carry multiple connections. I think some Apple connectors can have up to 4 or 5 different segments, 4 or 5 different wires connected into the connector. The microphone connectors you see on the extreme left there are for multi where you have multiple pins, and they usually screw on. There's a ring that screws on that presses the male body of the plug into the body of the jack. Those are used for microphones typically, because for a microphone, uh, not only do you have the microphone element, the audio, in other words, but you have a push-to-talk switch and maybe other buttons. And you may want DC power going to the microphone also. You can see various adapter connectors in the center there that go between different types of audio connectors in this case. There are also coax adapters and D connector adapters and USB adapters. This DIN connector on the lower right is a variation on what you see for microphone connectors, and the difference is these snap into place, so you can just plug them in or pull them out with a little bit of force. So I think the miniature phone plugs are referred to as 3.5 millimeters. So now the contacts on a phone plug, the contact at the end of the plug is called a tip. If there's the connector, the contact toward the base of the plug is called the sleeve, and if there's a third contact, because of its shape, it's called a ring. So if you look at the phone connector in the upper left of the picture, you'll see that the first one on the left has a tip and a sleeve, and the second one, so it can only carry one audio channel, and the second one has tip, ring, and sleeve. You can see the little black separation, the little black insulation rings between the conductors. So, yeah, phono plugs and jacks or connectors are typically used for audio and video. And it says low-level RF signals and control signals, but you don't see too much of that these days. RF connectors. We're dealing with radio frequencies here, so RF connectors come in many different types. The most common you'll see in ham radio gear are called UHF connectors on the upper left, excuse me. And you've probably seen those if you've been around HF gear at all. And those are typically good up to, let's say, up to 2 meters or so. They aren't too lossy. But when you get to higher frequencies, then the connectors, because of the way they are, because of their mechanical properties, excuse me, can have higher loss, and they can also, this is something that we're going to talk about, I think maybe in the antenna session next week, but a transmission line has what's called a characteristic impedance. So if you were to look at a transmission line at any point, it would have the same impedance. And a connector can produce what's called a discontinuity. In other words, the impedance changes as it goes through the body of the connector. Now for HF, it doesn't matter too much, but for higher frequencies, it does matter a lot. So you see these other types. F connectors are what cable TV uses, and the advantage there is that the center pin is actually the center wire of coax cable. BNC connectors are very common for test equipment. SMA connectors, you'll see those. Well, you see those on handy talkies these days because they're convenient. And you'll also see those on some RF test equipment. The advantage there is that they're small and they work up into the gigahertz range very well. You'll also see N connectors, which is sort of a beefier version of a UHF connector. An N connector, you can see if you look closely at the male connector on the right there, on the upper right, you'll see that there's a center pin, and around it is a ring-shaped connector that is actually connected to the shield of the cable. And the reason for that is it minimizes the change of impedance going through the body of the connector. In the second row of the picture, and in the third row of the picture for that matter, you're going to see different adapters between different kinds of connectors. The most common ones you'll see in amateur radio are on the left there, UHF to UHF connectors. One is the double male and the other is called the double female. Typically, somebody correct me if I'm wrong, but typically the double male is called a barrel and the double female is called a bullet. And you use these, well, the double female you very typically use when you have two lengths of coax cable that you want to connect in series. And they will almost always come with male connectors on the end. So if you use a double female connector in between, then you've effectively lengthened your cable. And then to connect different kinds of cable connectors to test equipment, for instance, or to change cable type, to change connector type to connect to radio equipment, you'll see these other adapters in the second and third row. And there are even UHF to phono connectors, which are not very useful at RF, but they're good enough for some applications. And that doesn't mean that you can use audio cable to carry your radio frequencies, though. All right, so what do we got here? So each type of RF connector includes the connection for the shield. Usually it's the outer body, although on the end connector, you can see that there is a ring that's inside the outer shell of the connector. And I explained adapters before. So what you want is, and we'll get into this next week, I think, connectors should have the same impedance as the feed line, because if the impedance is different between the connector and the feed line cable, some of the RF power will get reflected back toward the other end of the cable. And this is something you want to avoid as much as possible. So as I say, for the high frequency bands, UHF connectors, whatever impedance discontinuity they might have, is usually the effect is small enough to ignore. Where you care about the continuous impedance through a connector is is it the VHF, UHF frequencies and up. And so now this says the UHF family of connectors. It's called UHF because it was developed during World War II to operate at VHF and UHF frequencies. And it's since the Second World War that better types of connectors for those frequencies have been invented. But the name stuck. And you'll also hear them referred to as PL259 for the plug and SO239 for the panel socket. And that goes way back to the Second World War too. And it says typically used up to 150 megahertz. And they have power handling capacity up to easily up to the 1500 watts peak that amateur operators are allowed. So it's partly tradition and partly convenience that you still see these on almost every piece of amateur radio, every amateur radio transceiver that's not portable. Yeah, okay. So I got this a little bit wrong, but UHF used to mean what we call low VHF now, low VHF, VHF, and so forth. But the idea is the UHF connector was good enough for what people used during the Second World War, and they stuck. So one of the problems is lack of weatherproofing. And if you look at UHF connectors outdoors, what you'll typically see is electrical tape and sometimes a plastic compound over the connector, over both the male and female connector to lock out moisture. They also don't have very good performance above 150 megahertz or above 2 meters. So N connectors address those drawbacks. They're designed to be used up to 10 gigahertz. BNC connectors are good up to about 4 gigahertz. And you will see BNC connectors on QRP gear, equipment that runs just a few watts. Partly because of the smaller size because QRP rigs tend to be fairly portable and small. SMA connectors are the small threaded connectors rated even higher than N connectors, and they're typically gold plated. You'll see them connected to GPS units, for instance. And to connect GPS antennas to GPS receivers. And for Chinese handy-talkies, you'll see variants of SMA connectors used for the rubber ducky antenna to connect it into the body of the HT. Okay, data connectors. I will say that the exam's behind the times. It's very common these days and something you should expect to have a computer controlling your HF transceiver, and the connection works vice versa too. You can operate and the transceiver will automatically send its operating frequency to the computer, and it will automatically get entered into your log for most logging programs. So it's for two-way control. D connectors, typically 9-pin D connectors, are used for RS-232 interfaces. However, this is a real 20th century kind of thing. These days, USB cables and connectors are getting much more common. So the model number of a D connector, well, a DB9 or DE9 refers to the number of pins on a COM port, And you'll typically see 9-pin and 25-pin connectors. But the interesting thing is they are disappearing. The D refers to the shape. As you can see, that's a 9-pin D connector. You probably ran into them with your older computers, like for instance, when you hooked up printers or modems. These days, USB connectors are very common. These are all the different kinds of USB connectors. The most common ones are type A, type B, which is also called a printer connector, and type C, which is sort of taking over everywhere these days. Europe has said that every new cell phone has to come with a USB-C connector, so they're getting to be pretty ubiquitous. And modern transceivers, quite typically, for instance, my IC7300, which is a model that came out, I think, about 7 years ago, to connect the radio to your computer, you just plug a printer cable, a USB printer cable into the back of the rig and plug the other end into your computer, and that carries both the control and both the control signals, I'm sorry, data used for control, which would be the equivalent of an RS-232 port, and digitized audio so that you can run digital modes using software on your computer just connected by a single cable to the radio. And that's really great because anything that reduces cable clutter is a good thing. So if you buy a computer these days, you'd be hard put to find an RS-232 port on it. So what people typically do is they spend 15 or 20 bucks on one of these guys. If they have an older transceiver, which if you're buying used equipment, you're likely to have first as a first HF rig. And this USB to CAT cable, basically, it's got a USB connector on one end, and inside the shell of the USB connector is an RS-232 converter that converts the serial USB signals to, which converts the USB signals, which are formatted at high speed to RS-232 levels and speeds. And on your computer, it looks like a serial port. And to the radio, it looks like a serial port. Now, these are commonly called CAT cables for computer-aided transceiver. And this was a standard that I think ICOM came up with first, where the transceiver would use RS-232 or a variation of it to talk to a computer and perhaps to other equipment. And we're not going to get into all of that, but this is the kind of thing that you're going to run into when you try and connect your up-to-date computer with your somewhat older, perhaps 20th century radio. Okay, so let's do some practice questions. We're almost done with this part of the evening. So what's a typical upper frequency limit for the low SWR operation of 50 ohm BNC connectors? 50 megahertz, 500 megahertz, 4 gigahertz, or 40 gigahertz? Guesses, anyone, please?
High power, so I'll guess 4 gigahertz.
Well, the answer is actually 4 gigahertz. Yeah, there you go.
I got a question on that. You just showed that was that 9-pin serial port, that
Yeah,
diagram you had, correct?
let
That
me go back.
connected the USB. If you went
This
back
one,
there,
this one, yeah.
that's a 9-pin on the right, correct?
That's a 9-pin cable, a 9-pin connector on the right. That's right, because
Thank you.
most ham radio gear from 20 years ago, give or take, uses that connector. Now,
Yeah.
I will say I will say that if you buy an older radio and want to hook it to your computer, and it makes it very convenient, that you will want to look at what kind of connector is on the back of the radio before you go buying an adapter cable like this.
Thank you.
Okay.
I use one of those on my rig.
Oh, geez. It's almost 8:30. I'm going to declare a break here. So let's take a break for maybe a short break for 5 minutes or so, and come back shortly. Start sharing. Yeah, I'm going to start sharing again. Where are we here?
Thanks, John, for explaining that too. Wes does a great job. You do a great job. I just had to get it in my mind about that center tap. Thank you.
Yeah, I thought that was a tricky one myself because I don't remember bridge being covered.
No, he covered it great. I just couldn't get
Okay,
it in my
I
mind.
couldn't remember. I might have
Yeah.
been.
Here we go. Slideshow. Okay, slideshow. Can everybody see the question about N-type connectors?
Not yet.
Yeah, not yet.
It
It's
says it's.
loading. There it is.
Yay!
Got it. Yeah.
Okay, there we go. All right. Oops. All right. All right. So which of the following describes a type N connector? A moisture-resistant connector, RF connector useful to 10 gigahertz. B, a small bayonet connector used for data circuits. C, a low-noise figure VHF connector. Or D, a nickel-plated version of the PL259.
By process of elimination, I would say it's A, moisture resistant.
Yep, A, and 10 gigahertz. That's the giveaway. That's true. The end connectors are designed so that you can leave them outside without any special protection. When we say bayonets, those little bumps that are sticking out from a BNC female connector, those are used. The male you twist on and it locks into place because the sleeve has grooves in it that slide onto the. Well, as a matter of fact, if you know what a bayonet mount camera lens is, it's the same principle. Where there are little prongs little bumps that stick out, and the idea is in the mating part they lock into place. Okay. Anyway, yeah, the answer is A. What is an SMA connector? Type S to type M adapter, a small threaded connector suitable for signals up to several gigahertz, a connector designed for serial multiple access signals, or a type of push-on connector for high voltage applications.
You'd have to see one, I guess.
Okay, the answer is B. It is a small threaded, it's a small screw-on connector. Of the types of connectors we talked about tonight, the SMA connector works up to the highest frequency range. Even better than N connectors. Which of these connector types is commonly used for low frequency or DC signal connections to a transceiver? PL259, BNC, phono, or type N?
Huh.
And to answer this one, you have to ignore my opinion.
Well, you would say type N, wouldn't you?
No.
I'll be no BNC.
Phono?
Yeah, phono.
Yeah, the answer is phono connectors. Yeah. They are kind of going out of style, but yeah, that's a reasonable answer, or the most reasonable answer. One of the things is all three other kinds of connectors are designed for RF, and the phono connector is not.
Yeah, they're simple.
Okay, so I'm going to zip through. Uh, test equipment here. There are pictures of all of this stuff in the book, and I'm just going to talk very briefly about what all of them do and how they're used in ham radio. So a voltometer or a multimeter is what you typically use for measuring AC and DC voltages, as well as current and resistance. And they come in analog and digital. Well, everything comes in analog and digital these days. Sometimes some of them will test diodes and transistors. Some will can act as a frequency counter. Some can measure capacitance or inductance. Some of them will talk to your computer. But in the simplest form, okay, and digital multimeters offer greater precision than analog meters. The reason is, if you're looking at a meter with a movable, there's only a certain degree of precision that you can print on the face of the meter. Whereas a digital multimeter, you have separate digits, and so you can add as many digits as the precision and accuracy of the meter allow. So they're also analog meters are good for finding peaks and minimums, but if they're short term, but digital meters, but meters in general are used to adjust something so it's at a maximum or a minimum or at some fixed point. This is opinion. Experienced hams often prefer analog meters because it's easier to tell what's going on when you see a needle moving than to look at digits changing on a digital meter. Same thing with a speedometer. I know a lot of people prefer analog dial type speedometers, and I know a lot of cars, including my car, including my two cars, have digits only, which sometimes makes it difficult to figure out how fast you're going. Now, meters should affect the circuit that they're measuring to the smallest degree possible. That means, if you remember Ohm's law, when you're measuring voltage, you want high impedance at the input of the meter, because you're measuring the voltage across 2 points. You want to minimize the current flow. So if the current I is equal to E over R, to minimize I, you want to maximize the R. For current measurements, you want a minimum impedance in the meter, because current meters are connected in series with the circuit, and so you want the minimum voltage drop possible. Now, here are a couple of pictures just for the hell of it. On the left, you can still buy analog meters, and as you can see, they have multiple scales on the meter, but just one analog meter movement where current is converted to a magnetic field, which moves the needle. And on the right is a digital meter. It's got either 2.5 or 3 digits accuracy. Okay, it's got 2.5 digits accuracy, and I'll explain that in a moment. But these are things you can buy for 10 or 15 bucks off of Amazon, and they are actually pretty good for ham radio use. Now, when I talk about the number of digits, if you look at the scale there, you'll see, well, for DC volts, for instance, in the upper left quadrant of the faceplate, you'll see that most of those ranges start with a 2. Most of them start with a 2, which means that which means that the meter can count up to 199. So that's called 2.5 digits because you get that extra. Instead of counting to 99, it counts to 199. And that's very common. That's very common, and it's useful where you want to measure something that varies above and below something divisible by 10. Um, some meters, some digital multimeters will also do what's called auto ranging, where there are not separate settings for different voltage or current ranges or resistance ranges, but instead it will just say DC volts, AC volts, DC amperes, and the meter itself will figure out what the measurement range should be. Those cost more, but these things you can find. These things you can find, especially the digital ones, you can find for fairly cheap these days. An oscilloscope, I think you know what an oscilloscope trace looks like. I'm not going to spend a lot of time, but excuse me, but you can control how fast the display sweeps across. So you can measure timing, and you control how large you control the vertical excursion of the trace, so you can measure voltages. And so the vertical gain is also called the sensitivity, and it can go from hundreds of volts down to millivolts. Now, it used to be that some people would sample a small part of the RF coming from their transmitter and look at it on a scope. So if you have a homebrew transmitter, or if you are trying to adjust your transmitter, it can be very useful because you can see when things look right and when things don't look right. Excuse me. That's not very common these days with modern transceivers because they just work right out of the box, and you won't see very many monitor scopes in ham shacks these days. But I wanted to show you a couple of pictures. On the left is a Heathkit monitor scope that goes with their gear from, I want to say, probably the 1970s. And people would actually put kits together, put these kits together, and look at their look at the quality of their transmitted signals. Now, these also sometimes could be used for tuning, for tuning radio teletype. You may remember the digital mode tuning that I showed a few weeks back, where you would see a cross that would rotate, and you wanted it to be full vertical and horizontal and not skewed. I believe that this scope will also display that. Oscilloscopes, you've probably seen oscilloscopes that are big because they had cathode ray tubes in them, and the CRTs needed depth. Nowadays, oscilloscopes are digital. So these inputs are digitized at very high rates, and then they're displayed on LCD screens as though they're continuous, which means that you can buy scopes for a few $100s now that are, for a few $100s and up now, that are all front panel and very little depth. So this is what a modern day oscilloscope looks like on the right-hand side. To measure impedance and resonance, there are things called antenna analyzers, which include a very low power signal generator, sometimes a frequency counter, often a frequency counter, an SWR bridge, sometimes an impedance meter. And these come in a couple of different flavors. They connect to the feed line of the antenna, so they measure SWR and impedance without needing a separate transmitter. You can also measure characteristics of the cable you're using. You can find faults in the cable, things like that, and we won't get into that. But it's very useful for adjusting and diagnosing adjusting antennas and diagnosing antenna problems. And some but not all antenna analyzers can be affected by strong signals nearby. So if you are near another ham radio transmitter, or if you're near a broadcast transmitter, that can throw the readings off. These are a couple different antenna analyzers. The one on the left is sold by MFJ, and they have, unfortunately, they're going out of business, but they have a whole bunch of different models, and you can adjust the frequency with the knobs on the bottom there. And there are two different meters, one for SWR and one for impedance. And also there's a digital display near the top. So you get the best of both worlds, so to speak. And you can see the UHF connector at the top. You typically will connect that to your antenna cable. On the right is from a newer generation. Rig Expert, which is from Ukraine, makes a bunch of different antenna analyzers, and those are much more digital, and they will allow you to do things like show both the resistance and reactance of your antenna, components of your antenna impedance, and they will also sweep across a range of frequencies, so you can see at what frequency the minimum SWR of your antenna is. And those are even more convenient for making antenna adjustments. So on the left is mostly analog, and on the right is mostly digital inside, although it's still a low power RF signal that goes to the antenna. Field strength and power meters. Field strength meter detects ambient RF in the air. So you can use a field strength meter to see relative strengths of RF by walking around your antenna. An RF power meter, okay. And you can make crude measurements of radiation patterns of an antenna by walking around a fixed antenna or standing in one place and rotating the antenna itself. Now, the thing is, it's very difficult to calibrate a field strength meter. So the ones that you find will usually just give relative indications of how strong things are without any absolute numbers. In other words, you don't know how many volts per meter the RF field is at any point near the antenna. You just know where it's weaker and stronger. Our power meters are watt meters that work at radio frequencies and are put in line with the cable, with the antenna cable between the transmitter and the antenna. Most RF power meters will measure both forward and reflected power, and you can calculate SWR from that using that formula there, which I don't believe is on the test, but that's one way to calculate SWR. Standing wave ratio, and standing wave ratio affects how much power is transferred from your transmitter to your antenna, or from your antenna to your receiver. And we'll get into that in future weeks also. But the idea is a directional watt meter can measure absolute levels of power in the cable, but not in the air. So these are what they look like. The field strength meter is just an analog meter with a sensitivity control and a little antenna. And as I say, it's not really calibrated, but you can see changes in the RF field. The and on the right is a Bird RF watt meter, and uh, excuse me, the that circular thing in the middle is the sensing element, and to read forward power, you turn it with the arrow one way, and to read reverse power, you turn the arrow the other way, and that is calibrated so that you can read the number of watts on the meter. And as you can see, you can multiply that out too. Uh, uh, bird watt meters are sort of the standard for amateur radio RF measurements, but there are cheaper and newer RF watt meters that work just as well or nearly as well. And if you think about it, an SWR meter is a form of RF power meter, but usually it's adjustable so that the forward power you adjust to 100% of the meter reading, and then the meter is calibrated in SWR when you read the reverse power. Anyway, that's what these look like. So some practice questions. What item of test equipment contains horizontal and vertical channel amplifiers? An ohm meter, a signal generator, an ammeter, or an oscilloscope?
Oscilloscope.
Yep, D, an oscilloscope. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? A, a scope uses less power. B, complex impedances can be easily measured. C, greater precision. Or D, complex waveforms can be measured.
D.
Yeah, the waveform.
Yeah, D delta, especially because I'm showing it already.
Well,
Yes.
I didn't see that. I had it in
Yes,
my mind.
you can see the waveform. You can see voltage peaks much easier. You can see if there's funny business going on. Scope is very useful for visualizing radio frequency waveforms. Okay. Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? A, an oscilloscope. B, a meter, side tone monitor, or a wave meter?
A.
Yeah, an oscilloscope. And you can still find monitor scopes that are meant for this purpose specifically, or you can rig up something fairly easily to take a small sample of RF coming from a transmitter and make it the input to an oscilloscope. Okay, what signal source is connected the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? A, the transmitter's local oscillator. B, an external RF oscillator. C, the transmitter balanced mixer output. Or D, the attenuated RF output of the transmitter?
D delta.
Yeah, D delta. The reason it says attenuated, pardon me, the reason it says attenuated is because an oscilloscope can handle milliwatts of input, and the output of your transmitter is likely watts. So you need to either attenuate or sample the RF power output of your transmitter. Why do voltmeters have high input impedance? A, improves the frequency response. B, allows for higher voltages to be safely measured. C, improves the resolution of the reading. D, decreases the loading on circuits being measured. Anyone? We're talking volts and ohms here. That should tell you something. All right, the answer is D. You want a high impedance input on a voltmeter so that you want high impedance input on the voltmeter so that you load down the circuit at a minimum, or in other words, you divert a minimum amount of current into the meter. What's an advantage of a digital voltmeter as compared to an analog voltmeter? A, better for measuring computer circuits, B, less prone to overload, C, higher precision, or D, faster response?
Higher precision.
Yep, absolutely, higher precision. When is an analog multimeter preferred to a digital multimeter? A, when testing logic circuits, B, when high precision is desired, C, when measuring the frequency of an oscillator, or D, when adjusting circuits for minimum or maximum values.
I would guess D.
Yeah, it's D because you can see what's happening continuously, and it's a good visual indication, that meter swing, that you're getting more or less, higher or lower voltage. Which of the following can be determined with a directional wattmeter? A, standing wave ratio, B, antenna front to back ratio, C, RF interference, or D, radio wave propagation? All right, the answer is A, standing wave
A.
ratio, because that's a ratio of, it's a ratio derived from forward power and reverse power in a cable, or going to and from an antenna. Which of the following must be connected to an antenna analyzer when it is being used for SWR measurements? A, a receiver, B, a transmitter, C, an antenna and feed line, or D, all of the above, or any of the above?
We got to
C.
detect your antenna.
Yes, it's
Yeah.
C. An antenna analyzer is self-contained, so all you need to do is hook up the antenna. Or usually, unless you like to go way up in the air, usually just the feed line. What effect can strong signals from nearby transmitters have on an antenna analyzer? A, desensitization, which can cause intermodulation products that interfere with impedance reading. B, received power that interferes with SWR reading. C, generation of harmonics that interfere with frequency readings. Well, we didn't cover this exactly, but what do people think?
B.
You mentioned the radiation that it gives off. Is that what it's measuring?
No, what an antenna analyzer measures is basically the impedance match of an antenna to what you desire. In other words, usually 50 ohms, or the actual impedance of the antenna at a given frequency. So the answer is going to be B, received power. It interferes with SWR readings. Now, as I say, there's some slightly fancier antenna analyzers that act like radio receivers, and not like fairly dumb meters. And those can reject radio interference, strong signals coming from nearby. Which of the following can be measured with an antenna analyzer? A, front to back ratio of an antenna. B, power output from the transmitter. C, impedance of coaxial cable, or D, gain of a directional antenna?
You're measuring the coax cable. So I would say C, the impedance.
Yep, that is right. C, measuring the impedance of coax cable.
An S meter. We talked about an S meter in the early chapters. I'm surprised they didn't have that in this chapter. How come they didn't include the S meter with the antenna analyzer?
Um, because an S meter is usually built into a regular receiver. Well, it is built into a regular receiver. That's its purpose is to indicate received signal strength. But an antenna analyzer is it measures the properties of antennas.
I understand.
S meter
I just
doesn't.
thought, all right.
Okay, and that's it. So it is 9:03, and we have unfortunately used up all of our time for. We never got to the review, so the three instructors will have to figure out something to do here. But what I will ask you, the students, to do, if you please, to send an email to the three of us and tell us what parts of chapter 4 are the hardest for you to figure out.